Okay, hello again. DI504, Foundations of Deep Learning. Last week, you remember we did some coding, and I guess it was good for all of us. I mean, if you're trying to get used to practical coding in using deep learning at PyTorch. This week, we are going to do a similar example. We'll be coding a project, but this time in LSTM. So this time a sequence model. We have discussed sequence models in week 8 and week 9. So you'll remember them. LSTMs were one of the sequence models there, and they were capable of processing sequences. So what does sequences mean? We are going to talk about today. So this is an LSTM project, and we're going to be doing line by line debugging, and I don't have to tell you, the code is available at Auth2 class. Okay. The problem is word tagging. What does this mean? The input will be a sequence of words. So it will be a sequence of tokens, or NLP people call it that, tokens. Words are tokens in a sentence. So sentence is a sequence of tokens where the tokens are words. So don't think of this as different layers, guys. It looks like though, but what you see here is you feed the first token to this network. This is a single network, okay? So this is a single network, this one. So it is, the network looks like this actually. There is no other, so this is the end. I'm going to talk about what is an embedding layer is. So the LSTM. And the fully connected layer, linear layer, means the same thing. So you feed something to it and you get an output. You feed another thing, so you get another output. You get another thing. The thing is, FC, the fully connected layer and embedded layer, they just have some weights. They don't have a memory. So they just calculate. They are feed-forward neural networks. Remember from week 8. However, LSTM, anytime something passes through it, anytime there's a forward pass, it has some variables inside it, and they change, they evolve. So it is like the variables of the LSTM change. Like it has a memory, like the state of the LSTM changes. So what happens is, you feed something, it says the. Then you feed another thing. This time the layers, this layer and this layer are exactly the same. However, this layer is not exactly the same. Things have changed. That's why we have an arrow here. We don't have an arrow here. We have an arrow here, which means the things that have changed within the LSTM was passed for the next input. That's why LSTMs are sequence modelers. And this is a sequence to sequence problem. What is the problem? I just said word tagging. Very simple. In a sentence, we are going to tag the words as, I mean, according to the grammar of English language, as adjective or noun or verb or a determiner. The is called sometimes determiner. And we're going to do this in a supervised manner. Before we get into the code, get our hands dirty with the code, maybe we should ask, is this a sequence problem? Because if you ask me, is apples a noun? Well, it is a noun in any sentence. Yes. Is are a verb? Yes, I mean, it is a verb in any sentence. So maybe we should question the fact that this is a sequence problem or not. What is this? Any thoughts? Is this a sequence problem? Or maybe we are just tiring ourselves because it is not a sequence problem. And if it is a sequence problem, why? Anybody cares to answer? Or maybe speculate on why it would make a sequence problem and how it would make a sequence problem. No speculations?
Hocam inputların length'i yani variable sized.
Okay.
Ama outputlarımız classification gibi.
Well,
sequence problem ama
your friend is saying, well, we have varying length input, so that must be a sequence problem, she's saying. But maybe I should answer that question like, if you had a feed-forward neural network, only a feed-forward neural network like this, you could call that feed-forward neural network any times you want. So why am I accumulating a state within the sentence? Is there a reason for that? Thank you for the answer, though. Anybody want to speculate?
Cümlenin içinde bir akış olduğu için olabilir mi? O kelimelerin önetisinin bir anlam yaratıyor sonuçta.
Okay, your friend Ece is saying that there's a flow within the sentence and there's an inherent meaning within the sentence, which makes it a sequence. But can you give us an example for this problem? I mean, will the flow within the sentence make a difference at the classification? If so, yes, that's a sequence problem. Can you give us an example? Or I'm going to make the question easy for you because Ece, what Ece said was quite correct. Well, imagine there is a word that is classified as noun. Apples will be classified always as noun, and R will be classified as always as verb. Can you think of a word which will be classified in according to the flow of the sentence? For example, you have a word, you don't know how it's going to be classified, but when you read the word, you understand how it is classified. Can such an example exist?
Hocam, actually, I think red is like that.
Yes, definitely.
In this sentence, the red is adjective because of the red apples,
Yeah.
but we can use red in a different sentence, like this color is red.
Exactly.
Then it's noun.
It's like a noun. Maybe the reds are good, kind of. You're mentioning something. You're definitely right. So it is a sequence problem. Maybe it's a weak sequence problem, but it's still a weak sequence problem because the classification is obtained from this sentence. However, I'm going to continue speculating. For example, when it's the red apple, you're feeding it and you understand if it's an adjective or not by looking at the entire sentence. Berna said that because it's red apples, I decide, but in this flow, I classified red directly before I am the network. I accepted this input apples. Maybe this is a type of a sequence problem where LSTMs will not be sufficient. Maybe I should have used a type of LSTM which takes the input in both directions from start to end and from end to start. Do you remember such a type of LSTM? Maybe we briefly discussed. There is a type of LSTM called the bi-LSTMs, guys, bi-LSTM. So what I'm trying to say is, depending on the type of problem, you will decide if this is a sequence problem, and depending on the nature of the problem, you will decide which type of a sequence model to use. In my opinion, it is better to use a bi-LSTM in this case. Okay, enough for speculation, because this is a toy example and we are going to be constructing this network with very little number of examples, so it's just going to be a toy example. And you can always work on it, change it from LSTM to BLSTM, because in PyTorch we have BLSTM already in the libraries. Okay, I think we got the problem. Maybe we could just jump to the code now. Guys, this code is something I borrowed from PyTorch tutorials. You can always find it in the PyTorch tutorials. So let me show it to you in PyTorch tutorials. So it is here. It's just this PyTorch tutorial. It explains itself, but I think it requires a bit more explanation when you're trying to code it because there are many details maybe you aren't aware of. I'll try to do that for you so that when you're coding your own projects in this course and in life, it will be easy for you. So this is an LSTM for part of speech tagging, and the author is this guy from PyTorch. I don't know, PyTorch is an open source thing, so it could be anybody. Okay, now I've parted the code in three main parts. I mean, there are three main parts in the code. I'll start with the data and the problem definition. Okay, there's a class, there's a function here. There's a function definition. I'm going to skip it. I'm going to get back to this function definition when it's called. It's called somewhere down below here. Okay. I'm going to get there because it's just doing something for us, and I'm going to tell you by input-output relations. The first thing that I'm going to talk about will be the training data. So the training data is like a dictionary. You have a sentence, and this is a string because when you put something in between these double quotation marks, it automatically becomes a string. And for the string type, we have the split function, which will split the string into the words automatically. So if you just get it, I'm going to do that for you. So as you can see, it creates this. So the first part will be the splitted words, tokens. The second part will be my labels. So I'm creating a supervised training set where the is the determinant, dog is the noun, but denoted by NN, 8 is the verb denoted by V, the is again the determinant denoted by that, and apple is a noun denoted by NN. Why I'm using these? I want to use them because that's the example. These guys use that. That's why I didn't want to change that part. Where is that part? Let me show you that part. Yes, it's here. But I've added sentences. So there are 5 sentences. If you just take this and just run it on command line. So the training data is just simply a kind of a dictionary where you have the training data. When you create this type of data, it's a strange type of data. It is, if you take the first element, it is the first double, so the sentence and the annotations. So if you take the first element of the first element, it is the first sentence. The second element of the first element is the annotations of the first sentence. Okay, so I'm trying to show you how you just reach those values. Okay, so the guy is creating another variable here, word to index. What it is going to do is, since this is my training set, I will treat this problem like these are the words in my language. I mean, there are many words in the English language, but what this piece of code does is it is going to create a vocabulary for me, which includes only the words that exists in my examples. So let me do it. Let me just run that part of the code and you see, because there's this print and I'm going to get that part. So, okay. I jump there to training data, word to X, and I'm going to jump here. So I get the printed version. So I've got 16 words in my vocabulary. I mean, it's not counting the same word twice. It is the vocabulary. And they are indexed by integers. So the is called 0, dog is called 1. But it's a very, very lame vocabulary because it indexes the with the low capital D as different. Well, that shows how simple this example is. This is not something we would want, but it is. We are not handling it. Why not? Because we are doing that. It is a toy example. I mean, we could handle that. We are not handling it. Okay? So this is my input space. My tokens are indexed with integers, and I've got 16 different tokens. Okay? And this is my label space. So I just created where I've got, in my examples, 4 labels. Again, you might say that, well, there are other things in an English language, prepositions, for example, like for, into. Well, we don't care. This is just a toy example. You can always extend it. You could put those, you could put sentences with prepositions and label them. And you can increase this thing here. Actually, I've done it. The original example did not have adjectives. So if you can see, the original example did not have adjectives. I've added adjectives so that it would make an actual sequence problem, because the original problem did not require any sequences. If you have 3 labels, you can just do it without a sequence as well. Anyways, I tried to change the problem to show you that how you can change it. And I've got these embedded dimensions and hidden dimensions. These are the variables of the network. I'm going to explain you the network, don't worry. This is the data. So I've created the data. So the important thing that we should learn about creating this data is we created indexes to tokens, because in NLP or any type of sequence modeling using categorical data, this is categorical data because the input values are some categories or tokens, token-wise data, I should have said. I mean, words are not categories, but it could be categories. So they are not like numbers. They are not like values. They are tokens. When you work with tokens and when you have a sequence of tokens, the way you do it is actually you assign them to indices, these are index values. And the problem with treat these integer indices as arbitrary. I mean, the word being 0 and the dog word being 1 doesn't mean anything. I mean, they stand together as 0 and 1, close to each other, doesn't mean anything. So they are not values. They are indices, arbitrary indices for these tokens. Okay, so that's how you create your data. Good. Any questions about the data and the problem definition? Because we are going to be continuing to the model. Any questions? No? Okay. Now, the model. I'm going to be going for the model. Okay. So I've got a class here. Actually, this is a definition. That class definition will be used here to create an instance of the class. Again, very simple software engineering, guys. In object-oriented programming, you create these class definitions. I mean, for some of you, this is so trivial, I know, but for some of you coming from a different background, maybe you're confused with that. When you have a class, it is like a template. For this template to be realized, you create an instance of that template. So this is like a template. It's just a formula. But when you have this line of code, you are telling the computer to create an instance, a single realization of that template in its memory, given these parameters. Okay. And what are those parameters? Let me just show you those parameters first. I'm going to open the variable explorer. So embedded dimension, I cannot see that. Let me just write it here. Embedded dimension is 6 because it was 6 here. So hidden dimension is 6. Length of the word to X, which means the length of this dictionary, which you already know is 16 because I got 16 different words indexed from 0 to 15. And length of the label dictionary, which is, you already know, is 4 because they are indexed from 0 to 3. With these variables and using this template, it is going to create an instance of this model, which is a child of PyTorch neural network computational graphs. So it's creating a network. What kind of a network it's creating? The network it is creating is actually the one that I just showed you. I mean, actually, there is one I'm going to show you. There's a softmax here. There's that softmax. I didn't show it, but didn't want to confuse you. I'm going to show it to you. So it has 4 layers: the embedding layer, which I'm going to be talking about right now, the LSTM layer, the linear layer, a fully connected layer, and the softmax. Okay, so how does it create it? My drawings. Well, it's quite simple. If you remember what I just said previously, it was in PyTorch, when you create a network, a computational graph, there are 2 main parts that you need to write. The initialization part, where you define these nodes. So they are not connected yet. It is not a computational graph yet. You create the layers like nodes. And this is a variable, as you can see. It's a variable. But this is a layer because it's a children of the neural network library of PyTorch. And it's a type of layer which is called the embedding. We have talked about the embedding layer. I'll briefly mention the embedding layer, but if you're interested, where is it? Where is it? No, it's not here. In the other course, in the sequence modeling course I talk about these. So please visit this. I talk about torchain and embedding layer, how it works in detail. Okay, if you're interested, if you're an NLP guy, or if you're doing your project on sort of NLP using text or tokens, you definitely should learn embedding. Okay, embedding layer is for type of data which is not sensor based. Like if you're using images or if you're using sound, you usually don't use them. I mean, there are cases that you may have to use them, but usually no. But this is the type of layer that you use for tokens and text. How does it work? Okay, as I explained in this video, I'm going to explain it very clearly to you guys. So as you see, the input to our network is just these tokens. These tokens. So the tokens are first fed to the embedding layer. Since these are mathematical functions usually, I mean, when you feed something to the layer, it has to be vectorized. So at this point, my input values are indices. So if I'm feeding the, it is just 0. If I'm feeding dog, it is just 1. So what happens with a embedding layer is, I'm going to write it from top to bottom, so I'm not going to write it in horizontal direction or vertical direction. Let's say I'm going to feed the, and the index for the is, as you can see, 0. 0. Okay. What it creates it, so I'm going to feed it to the embedding layer. Okay, embedding layer. Embedding layer. What happens is, embedding layer inside automatically creates out of this index a one-hot vector. And when you're creating the embedding layer, it asks for the vocabulary size. And the vocabulary size, if you can see it here, is actually the value we said fed as 16. And it asks for an embedding dimension, which was the embedding dimension we fed as 6. The first thing this embedding layer does is, it takes this index and creates a vector of size 16 by 1, which is the vocabulary size. Okay. It fills this vector with zeros where the only one value is at this index. So it is 1, 0. It creates a one-hot vector out of this index and the vocabulary size. So it is feeding this vector to here. Okay. And it is just a weight multiplication layer. So in this layer, I have got 16 values, 16 nodes. And at the output, I will have 6 values, guys, because the embedding dimension is 6. So I have 16 by 6 connections or weights. So this is a 16 by 6 matrix. How I calculate the output is, there's a weight matrix which is 16 by 16, 6 by 16 times this one-hot vector. And here's your answer at the output. This is an embedding layer. An embedding layer takes an index value and a vocabulary size. It automatically converts that index to a one-hot vector, and it makes a multiplication with a weight matrix, which has this 16 by 6 size, which is provided to the embedding layer, and will provide you a vector of, if you calculate, this vector will be 6 by 1 of the embedding dimension. That's called an embedding layer. So why are you doing this? Very simply, you are carrying this one-hot representation to a space where your tokens are represented by a 6-dimensional vector of real values. So the output of this vector will be like 0.1 to 1.2 minus 2 point something, which is 6 by 1. Okay? This is called the embedding. I mean, embedding itself. The token is embedded with a vector like this. Why do we need an embedding? Why do I need an embedding? Because the reason I need an embedding is I'm trying to create a space where these words are aligned in a 6-dimensional space, and in that alignment the similar words are kind of closer to each other. That's the goal, and the network will train itself to do so. Remember, we had the D, capital D, yeah, the D with starting with capital D and D with starting with small caps D. Well, hopefully, when the network learns the embedding layer, it would automatically give embeddings to these two indices a similar value. So I'm just okay with that. That's why I didn't care if they had small case or the embedding layer will handle that for me. And if you're interested, please watch this video. Okay, I give the many details of the embedding layer, and after this video, actually, this is torch embedding, the theoretical torch embedding, and after this video, I have the coding for it as well. Okay, I just code and show you how embeddings work and how they can be calculated. Just watch that video if you're an NLP guy. If you're not an NLP guy, you don't have to. Okay. Okay then. So let me get back to the code. So we understand what the first layer is because the sentence is fed to the embedding layer. Well, don't care it's called a sentence. It's fed by token. A single token is fed first. Okay. The words of the sentence are fed. You're feeding it to the embedding layer. So let me draw the embedding layer as well. So the 0. So that's why 0, 0, 0, 0, 1. I mean, if this is the case. If, for example, it is not if it is, for example, let me say, let's pick another one to make things simpler for you. If it is 8 is here, then this is not 0, this is 2, then this is 0, but this is 1 because it's 0, 1, 2, and the others are 0. Okay? So let's see an example like that. Okay, so this is apple. It is 4. The embedding layer will automatically create a vector, a one-hot vector, 16 by 1, and I'm feeding it to the embed layer. Okay. At the output of the embed layer, the actuation is 6 by 1. Okay. Very nice. Then I have the LSTM layer. We talked about the LSTM, remember? The LSTM was a kind of neural network where it had recurrent connections. That was the part where we had the memory. Okay, very nice. This LSTM will have some hidden states. So it will start with some hidden states. The hidden state will usually start with zeros. And the size of the hidden state is also 6, guys. And this is where I designated. So LSTM create hidden dimensions with 6 and embedding dimensions with 6. Embedding dimensions is the input to the LSTM. Okay? So the input size, which must be 6 because I'm outputting an embedding size of 6 here, so they should be compatible. So the input to the LSTM will be 6. Anytime I feed something to it, the states will change. But this is 6, but this doesn't have to be the same. I could run this code by changing this part, for example, to 8. And in this case, I would have hidden dimensions, which are 8. So these two things doesn't have to be the same. However, the embedding dimension of the LSTM and the output of the word embedding must be the same because that's what I'm feeding from the embedding dimension to the LSTM. Okay? Very good. This is the LSTM. Every time I feed something, the hidden states will change values. I feed, and the hidden states will not be forgotten. So the hidden state will be the next hidden state. So that's the part of the memory I have. So that's the LSTM. Okay. And finally, I'm connecting a linear layer to the LSTM. This linear layer is actually a fully connected layer, which is a bunch of layers. And the input dimension is same as the hidden dimension because it takes the hidden states as the input. And the output dimension size is the target size. Remember what target size was? It was the dictionary size of the tags. So it is 4. So inside it, there's a weight matrix, which is 4 by 6, let's say, or 8, whatever this is. The hidden dimensions are 8. This is hidden dimension. So it is going to create 4. And these 4 values are actually scores for these classes. Okay, scores. These are the score functions for these classes. And those score functions are being fed to a softmax. Here is the softmax. Okay. So the tag scores are normalized probabilities, discrete probabilities, a probability mass function of this word being any of these classes. And these are the dimensions of each layer. So after the embedding layer, I have an activation of 6 times 1. As the output, at the output of the LSTM, the hidden states are the hidden dimensions. Let's make it 8, it becomes 8, or if it's 6, it becomes 6. And the fully connected layer gets 6 values and outputs 4 values, which are the values for each class. And the softmax creates these are the scores, and softmax converts the scores to probability distributions. Any questions about the model? That's how you read the model. Okay. I know they are trivial, guys, but when you start to code it yourself, you're going to experience difficulties, and going over a simple code like this will always help. So you have the chance to get back to this video and just see how I did it and how it's working, and kind of see anything. Okay, by the way, the debugger jumps because it is the definition. If you want to jump inside, I can jump inside it now, but I'm not going to. I'm going to create the model. So this is the model. This is a computational graph. So this is the model with these layers, guys. It's called the LSTM tagger. There's an embedding LSTM and hidden tag. The softmax is not included in the layers because I didn't create it as within the initialization as a node, because I don't have to. Why? Because I'm not going to learn that part. There are no learnable parameters. It is just changing the output to probabilities. I don't have to. If something is not learnable, you don't have to put it here because it doesn't have to keep variables for it. And it does. So this design doesn't. Very good. Now I designate a loss function. What was a loss function? In the end of this network, so this is the LSTM tagger. I'll be feeding a sentence, an index, and it's going to create a probability distribution for me, just like you had in the exam, 4 by 1, 0.7, 0.1, 0.2, 0.1, which adds up to 1. I don't have to tell you this. So this value will be compared to a ground truth. So what is the ground truth for this guy? The D is a determiner, and the classes are determiners. What was the classes here? So let me show you. These are the classes they are written here, as you can see. So noun, I'm writing up an verb and adjective. So the ground truth for this guy is actually 1000, because the is, if you know it, 100% determiner and 000. So I'm trying to find the loss between this value and the ground truth, and I'm going to be using negative log likelihood loss. What is negative log likelihood loss? I don't usually get into these details, but maybe this time. Negative log likelihood is just a mathematical way of putting the similarity between two distribution functions. So in machine learning, if you have classification problem, a multi-class classification problem, you can use many different loss functions. One of them cross entropy, one of them the negative log likelihood loss. What you do is you just, for example, this is another example. There are three classes. Let me get my pen again. So there are three classes here. The three classes are 0.71, 0.26, and 0.04. For this cat image, right? For this cat image. What is the ground truth for that? 1, 0, 0. What log likelihood function does is you multiply them. I mean, this is called Hadamard multiplication. So you do element-wise multiplication. So zeros doesn't count. You get the actual value, 0.71. You take the log of this value, and since this log value will be getting always a value lower than 1, because this is a probability, and you have only 1 in the ground truth, in every practical case, this value will be smaller than 0. And logarithm of any value smaller than 0 will be negative. And I don't want the loss to be negative. I want it to be positive, because I want to minimize the loss. Okay? I put a negative. So negative log likelihood. Negative log similarity. Likelihood is just a word like similarity. Okay? So you calculate negative log A, and which is something like this, guys. You're trying to minimize this. If you can make this 0, then good for you. So that's negative log likelihood, nothing else. So in a computational graph, if you can take the derivative of this guy, where you can take the derivative of this guy, it's analytically very easy. It's just like, that's like a division. So you can calculate it. You can calculate the backpropagation, and it's fairly an easy way of calculating the derivative for this function. It's a fairly easy way, fairly easy to calculate the derivative. So it is usually used. And for this toy example, is using negative log likelihood, guys. Okay, very good. I've got the negative log likelihood. Sorry, pressed the wrong button. I have to start everything again. Okay. Jump, jump, jump. I've got this, and I've created a loss function. Now I'm creating an optimizer, stochastic gradient descent. I'm the simplest one because of still this is a toy example. I'm sending my parameters, which are the default parameters. I didn't put any specific parameters, but I'm indicating the learning rate, which is 0.1. It's very fast, but this is a toy example. I'm going to overfit because you just cannot learn this problem with 5 sentences. You already know that. So I've got the optimizer. I have the optimizer. I have the loss function. I have the model. There's nothing stopping me to train it. And you have seen training. What this guy does is here, it just makes a simple run, a forward run, to see the tag scores. You don't have to do this, by the way. You don't have to do this part. In the example, in the original example, in PyTorch tutorial, the guy does it to show you that the initial values, the scores, are just random values. Let's do it. For example, what it does is, first says it's no grad. So it means I don't want you to calculate the gradients because I'm not going to be doing a backward run. I'm just doing a forward run. So while you are not calculating any gradients, do these operations. It means that's what no grad means. But while training, we don't use no grad. Actually, we use zero grads, which means first you initialize all the gradients and you accumulate during backpropagation. Okay, I'll get there. Don't worry. Let's do the forward run first. This is just to show you. Okay, then show us. It creates an input. What is the input? So this is the training data 0, 0. What was training data 0, 0? Remember the first example. So it is the first part of the first training set sample. So the first sentence, the dog ate the apple, split it into tokens. So this is a sequence of 5 tokens. However, remember, my network did not accept words. It accepted indexes because the embedding layer will want integer values, which will then it will convert them to these one-hot vectors, right? So I have to convert this into an integer sequence where how the integer sequence should be is, if this is the, it's going to be 0. If this is dog, it's going to be 1. If this is 8, it's going to be 2. If this is 3, it's going to be 3. And it's going to be 4. As you can see, since the vocabulary is created according to the training set, this is a sequence of indices 0, 1, 2, 3, 4. So the network only understands this input as integers. It is going to convert this input in embedding as input something like this. So the last one will be this. The embedding layer will do this automatically. However, I need to feed this into the embedding layer, not this token of sentences. So how am I going to convert it? I've written a very simple, I did not this. What was the name of the guy? Robert. Robert did it for us. He created this simple function, which is prepare sequence, which just takes a look at the dictionary, takes a look at your sentence, and outputs that value. If you just observe it, it's just the Python way of doing what I'm exactly saying. It's just taking a look at the dictionary and take a look at the sequence and getting the indices for that. Okay, because in the dictionary we had the indices already matched. So if you just do that, as the input, you have this sequence, just the one I said. And it's a tensor, a torch tensor. Because the prepare sequence outputs a torch tensor, it must be this type of variable because the model is a torch model, a torch computational graph. It will only accept the type of variable where it's a torch tensor. Okay, so I'm ready to feed it to my model. And I feed it to my model. Okay, so I'm feeding a sequence of 5. The model will be creating probabilities for these inputs. So let it do it. Text course. So some values, since the model is not doesn't have weights yet, it's just random values. It is not even probability distribution yet. So I've got this value. It runs it. So just if you want to see it how it works, I'm going to just I'm going to get into it and show you. So I'm going to jump here again. So now I'm going to get inside the code like this. So inside the code, just inside the code, jump here. I'm going to jump there. So I'm inside LSTM tagger. I'm feeding this sentence here. What was the sentence? 0, 1, 2, 3, 4. It's feeding an embedding. Okay, so the output of the embeddings, this value will be for each sequence value that I've got 5 sequences, 6 values. Remember, for a word, the embedding layer created a vector of 6. So for the first word, I have this embedding, and this embedding with random variables. So the LSTM out, I've got this value. As you can see, again, some values. And hidden tag, you can just check it this way. And the reason I wanted to put it is, I'm trying to show you how you can get inside the model to see the actuations in between. Okay? Okay, yes, we did. And the guy just here prints it and shows you that these are not just the values you're looking for. But now we're going to train it. It's going to train for 300 epochs, which is too much, but this is a toy example. Normally you wouldn't do 300 epochs. It's toy data. The guy Robert said itself. So for each sentence in the training data and for each label in the training data, you do this training. In training, what you do is you accumulate the gradients at each batch. At each batch is a sentence here. So you first initialize your gradients, you make them 0. Then you prepare the sequence, for example, like this. Again, this is the first sentence. So sentence in will be this again, because this sentence. And these are the targets. So why are these targets? Because the first sentence was, if you remember, the dog ate the apple. So it is determiner noun, verb, determiner noun. And determiner was 0, noun was 1, verb was 2. So the output is 0, 1, 2, 0, 1, 0, 1, 2, 0, 1. So I'm feeding that as well. So it does the forward pass. During the forward pass, the guy creates the actuation values, and using those actuation values, it creates the loss using the loss function. So I'm sorry, it just jumped here as well because I had this break point here. Let me jump to the loss function. It creates the loss. I got this loss. The loss value is usually not important, but I calculate the gradient for it. Now I do the gradient pass. Starting with the loss, I go backwards, and I have the gradients, and this line optimizes the weights according to the gradients. Okay? So I'm going to train it, and you see that there's training going on. Let me see this here. So let me stop it, and you see the training because it doesn't show the training. It automatically trains. Okay. I thought there are some print screens during the training, but we don't. I'm going to start and jump there. So we started, so it just printed the values, and it's trained now. Again, I'm going to test it. I'm going to test it with the same data, which was this, okay? So prepare sequence automatically creates the input values so that tensor, so I can feed it to the model. I feed it to the inputs. This time after training. Here it was before training, and this time it is after training to see if it is trained. These are the tax scores. Let's see if the tax scores are correct. Okay, so I've got. So we continue. Let me run the code to see these results. As you can see, I forgot to mention it. This is not a softmax, this is a log softmax, guys, which means you're taking the logarithm of the probability values. The output of a softmax is probability values. And if you take the logarithm, well, if the probability is 1, logarithm will be 0. If the probability is 0, logarithm will be minus infinity. So it's a negative value from 0 to minus infinity. Closer it is to 0, which means higher the probability. This is a log softmax. If you make this softmax, of course, this f is inherited from torch and functional. You will have probability values instead, as you can see. Now they sum up to 1. Let's not change the original one, which means the actual value, the true value is the one which is closer to 0. So if you look at these values, which one is closer to 0? This one. So for the first token, the most probable class is class 0. What was the first token? We are trying this sentence. The first token was the, and the was a determiner. And for determiner, the class label is 0. That's why we have 0, which is closer to, which is the least negative, closer to 0. So this is a true classification. So let's look at the second one, which is the most closer value to 0, this one. So the dog was a noun, and noun is 1. I'm not saying that this is training very well, but it's just overfitting, most probably. So the third one is here. So the dog ate. Ate is a verb. So 0, 1, 2, again, trained. And if you check it, this one, again, the, a determiner. And if you look at this apple, so it correctly classifies. So it is trained. I mean, it's not trained, it's overfit, but it's okay. So if you look at the values before training and the values after training, obviously the training loss decreases to a point where it learns or overfits to the system. Well, this is a very, very simple case of sequence modeling, guys. Even the problem is if it is sequence or not, we don't know, but it's a complete example at least. There are people who are doing this kind of stuff. I mean, this is very simple. You are doing more complex things, but you're most probably reusing codes. And sometimes when you're reusing codes, you don't know what's going on, what is going on inside the model, or what are the details of the model. So what I recommend is, just like I did here, you debug your model like this. Check the actuations, check the values, try to understand what is going on, check the loss values, or during training, check your gradients. This is how you do it. Any questions now?